Thank you all for coming. I know this is Friday afternoon, and I don't normally think about going to long talks on Friday afternoon, but I thought I would tell you a little bit about some of the work I got started on from that fateful conversation that Michael mentioned. I thought it was going to just take a couple of months and write a little white paper to the dean, and it's 3.5 years later and still going. This is an effort I got interested in through Michael and David Laudy, and builds a lot upon the experience of the UTeach program here at UT, and then thinks about how to take some of the methods from the UTeach program and address them toward how we train elementary school teachers in the country. So we started with a very humble view about thinking about a set of classes, and then started thinking a little bit more broadly about how we do teaching. And what I'd like to talk to you a little bit about is the nature of some of the classes that we developed, and then also some of my own personal experiences in thinking about instruction in a new way, and then how it's come to really impact what else I do here at the university. Because, to be honest, I mostly have given lectures throughout most of my life, and that's what I saw done in the classes I took as a student. But seeing a lot of the developments by others in the country about how we best go about training people, it's come to impact how I think about teaching myself. So this is a body of work that I'll start talking about mostly about elementary school education, but then I'd like to talk a little bit more about things a little more broadly than that. So where I'd like to start is what we do for people who are going to be elementary school teachers, and then talk a little bit about the kind of curriculum we developed to help train them. So the context here is that in elementary school there's a lot of good news and there's a lot of bad news. The good news is that in elementary school kids really like they start out liking science a lot. And if you look at surveys of children in elementary schools, there are all kinds of numbers that we should be really excited about. That 2/3 of kids like science. And it doesn't really matter if it's boys or girls. There's a lot of enthusiasm or self-reported interest in science. And that's something to be excited about. The problem is that somehow what we do in school manages to beat that impulse out of them. And that by the time we get to grade 12, aptitudes on various things that are measured, mathematics and science, seems to be gone away. And if we look a little bit further, what people ultimately end up majoring in, this is a chart that just shows number of degrees awarded to various disciplines as a percentage, what percent of degrees are awarded to women in various fields. And there are some of the biases in there that we all know very well. In physics, the number of women going into bachelor's degrees in physics is at the 20% level. And then you look at things like psychology, where the number of women going in, it's 70% or 80% of majors. We can't attribute that to just aptitude, because I don't think we all believe Larry Summers. It's Larry Summers, isn't it? But the trend here is rather incredible, and it's not. This isn't unique. There have been lots of past changes in enrollments in various disciplines. We talk about things like law school or business school. This also used to be entirely the realm of what men did, and yet there's all kinds of ways in which we've seen dramatic changes over the last 40 years. And so, we can think about things like even involvement in sports, where at a certain time it was only allowed or only supported from universities that we would support men's athletics. And the change of Title IX, dramatically changed that, of course. So we have to look at what it is we're doing for kids, and then, what it is the education system supports that results in the kind of sculpting that we see at the university level, where so few people are going into the sciences. There's lots of national attention about what it is that we need to be doing for elementary education in science, and some of the reports that get written are not very surprising. They generally advocate for why is it that we have education students learning their science as part of a big distribution course. So we have service courses in this department, we have service courses in astronomy and chemistry happening all around the university. And they generally pool education students in with the same group of students that are communications majors, they're liberal arts majors. And the question is, do these courses actually serve to train future teachers in science education? You can ask whether that works. And in those big classes, you have to look realistically at what are the kinds of instructional methods that are being used. We often teach in big lecture halls. And then you ask, does that result in a kind of training that we want for elementary education? And what is it we want elementary ed teachers to really be able to specialize in? So there are lots of issues there. And then the other issue that really comes up is, what is it that we typically do when we offer a course that's for the liberal arts major or the communications major and then pull that education major in? Well, typically we take the courses that we would offer our majors and then just tone them down a bit. And again, is it strategic what it is that we're doing for elementary ed majors? So I thought I'd talk a little bit about elementary ed majors here at the university, and at least as far as I've come to know them, it almost feels like we're talking about a laboratory system, but these are real people. I have to say, in my experience of working with this particular cohort and trying to think about how to design a curriculum for that particular cohort, this is amongst the more professional group I've ever encountered as a group of university students. Whereas most of our physics students, you think about them and they're saying to themselves, well, maybe I'll go to graduate school, or maybe I'll go get a job, and they're still really pondering what their ultimate career track is going to be. This is a group that, as a whole, is very aware of what their job is going to be and when they're going to be doing it. They're going to be doing it the day after graduation or the fall semester after graduation. Their time in college feels very concerted and targeted to them, and they're thinking always about their trajectory onto that job. So as a group, actually, it is a very easy group to work with because they're really working toward a professional education in a way that so few of our university students are. The other thing to say about elementary ed majors, which is kind of remarkable when you think about university students across the board, these are people who have decided to major in school. They like school. They want to be in school. They want to have their profession be school. So there's a strong interest, in a way, in their participation in these kinds of courses and in their own education that one doesn't get across the board with dealing with students at the university. And we all talk about we want to deal with major students in our own major because we think that there's a stronger, not just aptitude, but interest in the subject. The folks that are going through the elementary ed program have an incredible interest in what they're about to do because they know what their business is going to be at the other end of 4 years. So that's a really incredible and exciting thing to work with. And now the question is, how do we properly channel it? This is not a group, though, that comes to school with a strong interest in science. Their initial interest is all about kids. And so that's a very different focus from many of us who are faculty here at the university who came to our subject first and to teaching perhaps second. And we have to think about how to take the inverted nature of their interest and then harness that. So maybe it's known to some, but I'll just make a comment that so the folks who are typically majoring in elementary ed do a very split sequence of their 4 years here. The first couple of years are typically very focused on content courses. They're learning their psychology, they're learning their science, they're learning their math. All of these things are in some sense very theoretical in nature, and the last 2 years of their time is spent out in the field. They're really working on methods and practicum and field work within the school. So they tend to be two very different halves of the education experience. And of course, that's the exact opposite of the model proposed by UTeach, where one starts to talk about how is it that we get early field experience into content courses, because that tends to improve both how people learn content and B, it tends to improve how we focus content on the ultimate job that people have to do. So that's a structural problem that presents itself right away when you think about the elementary ed majors. They're not in our college, so we have less control over what their actual structure of the degree will be. Now I want to do something that almost feels like one of those terrible things you see on TV where people go up to the MIT graduates and poke fun at what things they didn't learn. And I don't mean to do this to poke fun, but I mean to sort of point to what are some of the issues that we look at when we're trying to deal with people whose ultimate profession is going to be to teach, and to teach conceptually, and to present information in such a way that starts to become intuitive to folks in K through 6. This is an example of a problem that is very representative of the kinds of things we would like a middle schooler or an elementary school person to know, and it just describes what makes a soccer ball move, and try to use words like energy and force in a relatively correct way to describe what's going on. And amongst both teachers and students alike, one will get the following kinds of answers. So when is the net exerting a force on the ball? Well, they can properly look at a graph like that and say that in section D of that graph, that represents the force or the influence of the net on the ball. But this notion of force is really tricky. And if one asks, when is the girl exerting a force on the ball, the most common answer stretches across time spans B and C. And the notions, the underlying explanations for this is something that we all know very well. It originates in that sort of Aristotelian view of motion, because that's the region, that region C is that region where the force of the ball on the ball is running out. There's somehow this notion that force persists. And ultimately, this is really an admixture of notions of force and energy that are at play, but it's also got this kind of Aristotelian, if you're not pushing on it, then it doesn't continue to move. And yet, when you look at what kinds of things we ask of students before they're allowed to graduate high school, these are kinds of questions that are on tax tests. And so these are kinds of multiple choice questions that we've drilled into people over and over and over again, and they do really well at answering them. So if you ask people, identify the place where the kinetic energy on a roller coaster ride is going to be the highest, they can do that, because that's a drill skill. That's not an underlying understanding of energy and force. And even questions with Newton's laws, although they're not maybe as successful, this is just a polling of elementary ed students here on campus, still the ability to divide force divided by mass gives you acceleration. That skill exists because, again, that's something we've drilled over and over again, and on multiple choice tests people can repeat that skill, but you still get the same group answering this kind of notion about what force is and what energy is. And that disconnect between what we sort of typically test on and what we value as an underlying skill exists across the sciences. So I picked a physics example first, but we can take this example that's a common demonstration. This is involving wetting two cloths, one with hydrochloric acid and one with NH3, and you stick it on either end of a tube. These things, when they combine, they make a salt. And so if you wait for a little while, you'll see a salt ring form in the middle of that tube. And it does so not at equal distance from either end, of course, because although the mean temperature of these two things is the same, the velocities aren't the same because the masses aren't the same. And so typically we go on in a chemistry class and we talk about where that salt forms. But even the underlying process of what's going on is something that's actually kind of interesting. Because if we try to model this, and this is something that at an elementary level we should really be valuing, if we try to model this, what we're trying to say is that there's this collection of particles. We'll call them molecules, but there's particles in there. And they're bumping around and they're doing stuff. And the mean free path is such that eventually one walks its way down to the middle of the tube and the other walks its way down the middle of the tube and they meet. But you ask some basic questions like, what's in between the dots? Well, they say, well, in between the dots there's air. But the dots are there to represent air. And so again, we're losing the forest for the trees if we fail to somehow convey what these little dots on paper are supposed to represent. This is another very basic example, and this is the one that makes TV shows, and again is used primarily to embarrass Harvard graduates at graduation time. But there's this very famous TV clip done by the Annenberg Foundation where they go and they hand a big chunk of a log and a little seed to some Harvard graduate as he's about to go up and get his diploma, and they say, by the way, what is it that makes this little seed grow into be this big chunk of stuff? Where does all the stuff come from? And then they start listing stuff, and they say, it's sunlight, it's this, it's that, and then the thing they never say is air. But of course, where does all the carbon in the tree come from? It's not that, and the very common misconception, of course, it comes from the dirt, and somehow you imagine these trees sucking up all the dirt around them and creating this big crater so as to create the tree, right? But that's not what's happening, it's photosynthesis. And yet, what we typically put on tests is what's on exactly our tax test here in the state of Texas. It's this chemical formula. And we have overemphasized the ability to recognize some chemical formula, but missed, again, well, I shouldn't say forest and trees because that'll come off like a pun in this context, but we've missed a very underlying thing, which is what is the physical process that's happened to transform molecular bonds into energy and vice versa. This one's my personal favorite because I actually have used it on friends before they stopped being my friends. And you start asking people things like, why is it that the moon is half dark at night? And little kids walk around and say, well, it's the shadow of the Earth. And then, again, you can get the Harvard graduate picked on at graduation time, and they'll say it's the shadow of the Earth. And in fact, even some of my dear friends who are faculty at this university, I've asked on camping trips, so what is it that makes the moon half dark at night? And they'll say it's the shadow of the Earth. This is a really hard one to overcome, and yet it goes back to a very basic geometric picture. Right? We're not in permanent eclipse throughout all but one day of the month. Right? So I think we're failing if we're not managing, if we're doing more Hertzsprung-Russell's diagrams with elementary ed majors, and we're failing to accomplish some of the basic curricula that they have to do. My chemist friends, their favorite question that we pick on is this one. So this is also a tax test question, and I'm going to put it on you guys. So which of these are composed of 2 or more different substances that are chemically combined in a definite ratio? And there are 7 choices there. You know, the first time I saw this, I have to confess, I thought the answer was molecules. Would anyone agree with me? Is it molecules? You're nodding your head. You're honest. Okay. Anyone else going to say molecules? Okay, there's a few physicists who are honest out there. So physicists typically say molecules. To a geologist, essentially everything under the sun is a mineral, I've learned. Whether it's a solution, a molecule, a compound, apparently everything's a mineral. Iron's a mineral as well as CO2 is a mineral. But a chemist apparently says it's a compound. Molecule is reserved for 2 similar things that are stuck together. So nitrogen is a molecule, but that's a specific case of a compound. I didn't know that. In any case, we get real hung up on a lot of our science testing for people on terminology. And remarkably, people can go through 2 different courses offered by 2 different departments and be talking about exactly the same content. And yet, if it's offered in departmental courses, it can be subject to the kind of jargon or implicit terminology used by one department and not used by another. And so, you know, it's maybe not so surprising that, you know, we can't necessarily poke fun at the layperson who says, oh, it's a solution, because, well, in some contexts, that's maybe a good answer too. But we can't get real hung up on it because this starts to get to be terminology. So we've tried to work on a set of curriculum in what we did in this project to really strip down to the basics of what we needed to do and use less terminology, because this is something we tend to do a lot in the sciences. We tend to invent a word and then spend a lot of time developing intuition about the word. So we all know what force is after years and years of accumulation of experiences with that term. But we've tried to work really hard at developing the experiences in the course rather than the terminology. And I think that's been a real eye-opener for me, because I fall prey to wanting to use words like work a lot in my classes, and that doesn't always tend to go well. And I have to convey again, the kinds of folks we're working with are the cream of the crop of the state of Texas. I mean, these are all people who went through high school and are at the top 10% of their class. And the kinds of things that we're seeing should be reflected upon as what our education system is designed to achieve, as opposed to what is it that's somehow an inherent indictment on the students that we receive. We have to look really hard in designing a curriculum that actually shoots at a certain goal. And so that's kind of what we were looking at when we designed this curriculum. And you know, as a byproduct, when we think about the fact that these are folks who came to their major not because they love science per se, but rather because they love kids, and then teaching science and teaching math is going to come along with that ride. These are the kinds of attitudes that are conveyed by some of the students in their classes. So what they've learned is what we learned in focus groups from them. They've learned that science is about getting the right answer, because you take multiple choice tests and you either get it right or you get it wrong and get slapped in the head. They've learned that science is mostly a solitary experience. You go study it over and over and over again. And they haven't necessarily learned it to be a creative process. They've just learned it to be about facts, right and wrong. And I have to look at my own career, and if I thought if anything looked like that, I would have not wanted any part of it. I mean, as a particle physicist, I tended to work on projects that were big, that had 200 to 500 people on them, because that was kind of a dynamic experience. And I tended to look at things where the right answer wasn't known. And in fact, that's the cool part about the experiment. Otherwise, we wouldn't do it as an experiment. and it's creative. I mean, that's the whole point of being involved in the sciences. So somehow we've managed to construct a whole K through 12 system that doesn't capture that very process. That should be thought of carefully. So we started with looking at the classroom model, and here I credit Michael Martyr because he was really pointing us to a lot of work that has been done on what are the kinds of classroom models that support trying to get that scientific thinking in students. So we can start with maybe not the right model, but let's talk about what our model is. Let's talk about this room. This room has its origin, it's a couple thousand years old. And it's an auditorium, which means it's meant to convey sound. You can hear my sound, and you get to hear it. You get to hear information come across the air. That's its primary function. And we still use that function, right? Our lecture auditoria don't look all that different. And the other word that comes into play is lecture. I mean, that means to read. And I think the underlying thing that's there in that model is that somehow I have some information that you all are going to be empty vessels and get filled up with that information, and you didn't know it unless I said it. And I suppose if this was, pre-Gutenberg early Christendom, and I was sitting there at the lecture pulpit in the front of a big cathedral, that would be true, because very few of you could read. But we don't have the kind of information scarcity that existed a couple thousand years ago. And there's lots of research to suggest that what's most valuable in an educational experience is not this kind of conversation we're having right now, and not the kind of things that we might commonly associate at a university, but rather the human interactions that take place when a student is at the university. Then we go back to that lecture hall, especially the ones I've taught in where I've really dulled my class to sleep, and I ask how much human interaction is taking place there. Okay. So we don't have information scarcity. It's been a long, long time since we've had the Gutenberg printing press. It's been an awful long time, even since the 50s, since we had the photocopier, and people have access to information they didn't used to have before. And it was painfully demonstrated that we live in the modern age and we have even more access to information. My own personal connection with this came a couple years ago. I was giving a lecture class, Physics 362L here, and I made the terrible mistake of writing a chemical formula on the board. Being a physicist, I should have never even dreamed to do such a thing, but I wrote down the formula for lead tungstate. I got it wrong. And some student who was a chemistry major got her iPhone out and was typing lead tungstate and said, "Professor Kopp, I think you're wrong." And I said, "Well, I'm a particle physicist. Of course I know this. I work with lead tungstate. I know what lead tungstate is." But she said, "Well, okay." And then she quieted down because I shushed her. And then a couple minutes later, she said, "Oh, but I've looked it up on my iPhone. I think it's really lead PBW4. See, I said 3. I knew it. In any case, I knew that my role had changed because I didn't have all the information. Students have lots and lots of information. And that's not our value added as instructors here at the university, because often when we write things down on the board, we're making minus sign mistakes right and left anyway. So we have to think about other things that we should be doing in the classroom, not just adding information. So there's this report that dates back quite a long time. It's 1969. And it kind of says all the things that are intuitive to us who are involved in graduate education. How do you really teach someone to become a PhD? You get them involved in doing their own projects. You get them involved in solving their own problems, and they're real problems. And if you can't do that, because that's expensive, and we know graduate education is expensive, then you try to replicate it on the small scale. Either you're trying to reenact it, or you're trying to simulate it, or you're trying to at least provide demonstrations of it. And if you've got to do the worst possible thing, you just talk about it. And I don't know if this triangle is really graphically correct, if it's really a nice, neat line like this in terms of information retained, but it's certainly a plausible trail-off of diminishing returns of what's the information retained by a student going through a class that's done in various methods. And I know that some of our most gifted instructors, even in our department, are not just relying on talking about it, they're doing a lot of things in their classes, even their lecture classes, to recreate things further down on the scale. And if that's not convincing enough, I'm going to resort to quoting Carl Wyman, because he's kind of like quoting Einstein now. If you really want to have a trump card and you want to say something about science, you quote Einstein. And if you want to talk about education, nowadays you quote Carl Wyman. So Carl Wyman sort of casts this process of education in a different way, thinking about some aspects of psychology, that our process of education is really about developing new connections in the brain that didn't used to exist, and making those connections solid so that we as students are able to actually not only have better memory recall of facts, but actually have better working knowledge of facts in the future. So if we start thinking about education as a process of making new connections or new pathways, that's a very different role than we think about when we just talk about lecturing in front of a classroom. So enter a number of groups, among them MIT, but others at NC State were really involved in this kind of work of completely redesigning classrooms. And one of the most famous examples was quoted here in the New York Times about a classroom at MIT. Carl and Roy will recognize Gabrielle Sciola there on the front page there. This was a classroom that was really unusual for its time because it had no front, it had no amphitheater, it had no lecture podium at all. It's a classroom filled with tables where students are supposed to do work. And all around this room are projector screens where they can share information up on projectors. At every table are the ability to plug in laptops or do experiments. And at every table are plugins for computers so that faculty can put simulations on the table or students can share information across tables. And the whole point of this set of classrooms is to create a dynamic working environment where people can actually simulate or do things on their own and then promote the kind of cross-collaboration amongst the entire classroom. So that's the kind of scene that that they advocate things should look like. We have now a couple examples of this in our own building here in RLM. We created 2 small examples with some funding from the college. One of them is 7.114 and the other is 116, right across the hall from each other. And they are classrooms that unfortunately have a big giant podium in the, a structural column in the middle, like one of these. But it's only I guess it's sort of a tangible reminder, we can all take it that way, that you're not supposed to be lecturing at the front of the room. The students are supposed to be working anyway. So what's typically going on is you have groups sitting in tables in groups of 4, and they're really conducting experiments, and that's the emphasis of the class. So I'd like to tell you a little bit about the specific curriculum we developed using this particular teaching model, and I'll tell you some of the key components of the learning aspect of the program, and then some data of what we've seen using this kind of inquiry-based format. So again, we're trying to do elementary ed education here, and so I'm going to focus on that particular curriculum to begin with. This is one in which we've tried to build a curriculum together that covers all the sciences. So it's not just a physics course, it's not astronomy, but it's got to encompass geology and earth science, it's got to do biology, it's got to do chemistry, and it's got to do astronomy. And we've tried to build it on 2 very simple principles. One is that concept of energy, and the other is the atomic nature of matter. And with those 2 principles, you can build up an awful lot of the sciences. And I think that's helpful to have 2 very simple starting points, because the moment we start throwing around lots of Latin words in biology class is the moment people are memorizing things rather than constructing models to explain things. So again, this is not a very advanced class from the point of view of mathematical framework, but rather what we've tried to do is to develop diagrammatic models that really construct that kind of idea for students. So one of these would be these kind of energy flow diagrams where you're looking at a system in a box and you're really trying to diagram what are the sources of energy in, what are the sources of energy that leave, and then what kind of changes in the system take place. And the other is to, at a very simple level, try to construct a relationship between macroscopic quantities and the microscopic description of nature. So we can diagram pressure as what it really is. It's a measure of collisions that take place and the energy per collision or the impulse per collision. And we can model things like temperature as average kinetic energy. And if we really can start to construct that parallel understanding of macroscopic and microscopic nature of things in students, then we can make a lot of progress on things like how to understand convection in the Earth, how to understand weather patterns, or how to understand buoyancy of boats. Why is it steel boats float and steel blocks sink? Okay. So a typical class in this curriculum really focuses in an entirely different way. We don't design a lecture, but much like the physical science classes that are taught here in this department, constructing a set of experiments that really guide the students through to the conclusion we would like them to reach. If the goal of the day is to teach that the buoyant force is all about the displaced water volume or displaced water mass, then we could try to construct a set of experiments that first show some things float, some things don't. Density seems to matter, but then density isn't the entire story, that you have to talk about volume of displaced water as well. And with every turn, with every concept that we really want to drive home, think about the set of experiments that we want the students to walk through and ask them to start modeling every step of the process. What is it that they learned from that experiment, and how does it build on what they learned from the previous experiment? This isn't exactly new territory for a lot of people, but it certainly was new for me to start thinking about what is the difference between a logical presentation in a class rather than what we really want to achieve, which is how is it that you would actually build a model based on your own observations, so that when the classroom eventually goes into discussion mode and talks about the set of experiments they did, they're using that collection of evidence as the set of arguments that they're going to use to construct their model. Another really important innovation was suggested by a group at Arizona State, and they call it whiteboarding. It goes by lots of different names. But at the end of a class, as suggested by this group, they typically had students go through a set of activities, and then in order to really have the students go through the process of arguing through a set of ideas and discussing amongst themselves, they literally put out sheets of whiteboard. Initially when we constructed this class here at UT, we went out to Home Depot and got some shower liner stuff, because you can make whiteboard material out of that. And we had the students go through a set of questions that we had devised in advance that they were going to answer at the end of their experiments, and ask them to share ideas. If they were going to talk through 5 strategic questions that were going to summarize the ideas of the day, the instructor was not going to answer the questions, but rather they were going to take turns providing each of their own answers and comparing notes. And then, as a class, started to discuss which things struck them as the most compelling argument to explain at an underlying level what was responsible for the results of the experiments they saw. In a mathematics class, this would look a lot like what R.L. Moore would have done, where he would have had students start to compare mathematical arguments at the chalkboard, except now we have little portable chalkboards. And more recently, we started to think a little bit about how to make this process scalable, because it is pretty compelling when you see it, and you see an entire classroom focused on, I've got my answer, you've got your answer, and there's somewhere in between is the right answer. It's pretty cool to see it, and you'd like to think about how do we make that scalable to bigger classes, because up till now we've only been able to offer classes as big as 50 people, and that's just technically what's feasible. When you're holding up a sheet of whiteboard, you can't see it for much further. So we started to look at ways to use technology to support this kind of thing. So now students are pointing at projector screens where their answers are projected on the screen. And to further enable that, we developed a second one of these classrooms where every table has a digital plug-in, so that iPads at the tables can be used to record student responses. So students could sit there and scribble on an iPad a particular mathematical argument or a diagram or whatever it is that they want to use to answer the question. And then the instructor sitting at a console can actually imagine this room is now filled with 3 or 4 projection screens around the room. The instructor can choose which table goes to that screen or that screen or that screen, and the class as a whole can see all these possible answers and start to construct a best possible answer using different student groups' input. And so that's a way where technology can help this process a little bit, because we can start to scale up to class sizes that are a little bit more practical at a big university like ours. The other thing we've done is really focused on what the assessment itself is in this classroom. And the kinds of whiteboarding exercises I mentioned to you before typically go under the rubric of formative assessment. You're just trying to get a pulse of what your students are thinking and use that pulse to shape their ultimate learning. But then you want to go to a point where you actually are testing them on something. And as we thought about the testing process and what it is we really wanted to reward in this particular cohort, we came up with one answer that's not necessarily universal, but seems very appropriate for the kinds of skills that we wanted the elementary ed majors to come out with. And that's a set of practical exams. And again, this isn't unique to our class, but it's done in many classes around the university, where the students aren't necessarily being asked to memorize and then be able to regurgitate certain information on an exam. They're being asked to demonstrate the same experimental skills that we've asked for in the class all the way through, and then be able to interpret the outcomes of those experiments. So test day is a pretty busy looking day because we set up stations around the classroom and ask students to go through several stations, much like you would ask students to work through several problems. And their test answers are then a completion of a set of ideas of what explained the phenomena that they were able to devise in their little miniature experiment. The other component of this course, and again, it's a very specific answer for this particular curriculum, but we as faculty will often throw around the notion that I learned a subject really well because I had to teach it last semester. We tried to put that into play with this particular curriculum. We asked these students to be involved in various outreach efforts with the local schools and actually teach some of the subjects that they were learning about in their classes. And as many as about 1,200 students per year have gone, or elementary kids per year have gone through the department in the last couple of years on field trip type days. And we thank the UTeach folks for coordinating this because they've had these kind of early field experiences built into their curriculum for the natural science majors for quite a long time. So we've tried to recreate that same experience for the elementary ed majors where the act of having to teach it really focused their attention on that particular day and being ready for that particular topic. And hopefully that has a content value as well because students actually start to say, I have to learn it for that particular day. So ultimately, students do have to learn something, and I wanted to share a little bit of information of what we've gained so far on what we're seeing in the students who have taken these classes. The two charts here are representative data from a couple different of our classes, one which assesses mostly astronomy and one which assesses mostly physics. And these are tests that were developed at the Harvard-Smithsonian Center by Phil Sadler's group, and they've been administered nationally. There are sort of a collection of information and questions that are deemed nationally important for elementary teachers to know or be able to master. And we administered these not as part of the course per se, but prior to instruction and post-instruction, just to see if the courses we were teaching managed to allow students to master some of the material that is deemed most important for elementary teachers. So actually, in some cases, we got these tests after we designed the course, and I think we could say with some safety that we didn't design the course around it, but certainly in the attempt of designing courses relevant to national standards for science education, I think we managed to do something that was somewhat in concert with what was devised on these assessment instruments. The horizontal axis on both of these plots is just the test percentage that students got prior to the beginning of the semester of instruction on a particular topic. And the vertical axis in percent is the score they got on the same test a few months later following the semester that they took that particular topic. And the green line, it doesn't look particularly green on that projector screen, but the green line in each case represents if you got the same score on the pretest as you did on the post-test, so you had no apparent change. There are a couple students that look like they lost information in the course of the semester, but most people seem to be above that line. And the red line that's in those graphs represents a best fit to that data. That fit kind of looks like Hubble's earliest fit to a Hubble diagram, and it kind of is a line if you squint really hard, but that's a fit. I guess that's why when statisticians report means, you should always be suspicious, right? You can graph that same information a different way. A quantity that's often used in the education world is called the gain. If you scored at 40% at the beginning of the semester, then you're not likely to score less than 40% at the end of the semester, and you have 60% of the way to go. And so the question for the course then is how much of that 60% did the student get to learn over the program of work? And so the gain is defined as the post-test minus the pretest over 1 minus the pretest. In other words, it's a representation of how much of that 60% did the student get. If you started out at 90%, you don't have a whole lot to gain in the first place, so we have to normalize that out. So what's plotted on the vertical axis is that possible gain versus the test that was achieved by the student prior to instruction. And I don't see any particular trend there. It looks like a gas to me, but we can try to average those numbers and say what's the typical gain achieved by students over the course of the semester. And that's what this chart is over on the left. It's the 4 semesters of our course. This is a relatively small sample since we just started administering these tests last January. And you see means and uncertainties on the mean prior to instruction, post-instruction, and then the gain in percent. So these gains are 30-ish to as much as 40%. And that's not an unusual number when you look at national averages in inquiry-based courses versus lecture-based courses. Often the lecture-based courses are down in the 10% range, and the inquiry-based courses are in that 40 to 60% range. So we could do better, but we're certainly doing better than a typical lecture course. The other thing that we did in the course of this kind of assessment program is we try to really tease out what's multiple choice guessing versus what do the students actually understand. Since there was so much of the curriculum that was built around getting the students to be able to explain things and be able to justify their answers using evidence, we asked the students at the same time they were completing these multiple choice tests to provide a short answer for why they selected the right answer or why they didn't select any of the wrong answers. And then we scored that separately. So that's a somewhat subjective thing. It's more subjective than just a multiple choice test. But it allowed us to at least look at answers that were things like, I remember this from high school, or I think that's what I remember, or that's just the way it is, as a wrong answer. And students who could say, well, this is the thing I was noticing is wrong about the other answers, or this is why I think this is the right answer, and tease out that kind of thing from guessing. So this chart here on the right is a regrade of that multiple choice test where we went through those short form answers and again graded right or wrong based on our evaluation of whether or not they could explain what was the right answer and could explain why the other answers were wrong. First thing to notice is that the means are all low compared to their ability to do well in a multiple choice test. That's not surprising. Sometimes our ability to do memory recall is better than our ability to explain something or be able to explain why it's so. And the second thing to notice is that the gains are also similarly large, with the exception of one class. We'll have to figure that one out. But anyway. The other comparison we made is to some other classes that are offered here in the College of Natural Sciences that were otherwise taken by elementary ed majors. So these would be things like Astronomy 301 or Chemistry 304 or Physics 309, I'm trying to think, Bio 301. All those would be sort of the companion courses. They would be the typical things taken by elementary ed majors were there not these new courses available. And in making this comparison, first of all, you'll notice that the gains are considerably different in those other courses. I don't want to suggest that there's somehow some form of superior instruction going in one case and inferior instruction going in the other case. What I rather mean to focus your attention on is if we're trying to achieve a certain expertise or skill set in the elementary ed majors here on campus by the time they leave, then one set of curriculum has been apparently more targeted at that goal than sending those students through a general curriculum that's equally taken by communication majors and liberal arts majors. I think that's probably the more proper conclusion to take from this kind of comparison. The student attitudes are also very interesting to me. When we conducted focus groups more recently, the kinds of things that students were saying about the courses, they still report science as a pretty hard and frustrating subject, but the kinds of things they were talking about the nature of science were actually pretty compelling. They started to get the idea that science is a collaborative project, and they started to get the notion that collaboration is important in order to form the correct idea in a science class. That's a significant victory in my mind. Or they started to notice that there are creative aspects to the sciences where it's not always obvious what the correct interpretation is, but rather we have to, as a group, develop the best model. Those are the kinds of things that I like to see. The other thing I wanted to tell you a little bit about is how we're trying to extend this particular curriculum out into the schools themselves. So it's fine to say that we're going to do a quote-unquote better job with elementary ed majors, but then once we send them out to the field, the ultimate goal is that science instruction should improve out in the elementary schools. So most recently, we've been able to develop a specific set of partnerships with 3 school districts, and I hope soon 5, south and east of Austin. And these are all school districts where the population flow from Austin out into the surrounding area has dramatically changed the population in those schools. So I'm thinking specifically of Hayes, San Marcos, Wimberley, and now Manor and Del Valle. These are all school districts that at one time were largely white, largely rural. And the school populations have literally doubled over the last decade, and the demographics of those populations have changed dramatically. I think I'm going to spare us some of the text in light of time here. Let me just call your attention to that table right there, because this kind of says in numbers what I was saying before. So these are 5 school districts that we're looking at working with, initially just starting with 3. And you can see that the population between 2000 and 2010 in the elementary schools has changed dramatically. So Del Valley has gone from 6,600 students to 10,000 students. Hayes has literally doubled in student population. And so these are rather dramatic changes that those school districts are confronting. And then furthermore, the nature of the students that are coming reflect the demographics as people are leaving Austin, which is becoming increasingly expensive. So you see the percentage of Hispanic students going up, or you see the percentage of economically disadvantaged students going up, or the English as a second language type students going up. That's a rather significant change for some of those school districts. So what we propose to do with these school districts is to develop a professional development program where we would be working with every single elementary teacher who does science and math in the entire district. So we're going to have to go a little bit smaller than that. In 2 of the districts, we're doing every single elementary school, every single science teacher. In 1 of the districts, we're doing about half of the schools. But the idea was to be able to, first of all, change how science instruction looks and also improve the content knowledge of the teachers, but then also be able to actually research the impacts of what we did. So actually, the second half of the schools in 1 of these districts is our control sample for right now, and we'll go over to working with that second half of the schools in a future year. But for right now, we're going to look at changes in the schools that we targeted versus the schools that we didn't. And each of the teachers will be put through a 1-week workshop in the summer. They'll be going through a workshop on either astronomy or on physics or biology, something very focused on content. And then throughout the year, we'll be working with them on the teaching methodology, how to actually implement the inquiry method in their own classes, how to actually look at some of the curriculum that they're handed by the school districts and view it in light of some of the content that they learned from us. And I think back to growing up. I grew up in the Midwest, so I always heard, growing up, the morning ag report from the State University of Iowa. I always had this picture in my head of the state universities being out there and present in the community. And this is, for me, kind of a fun experience because it's our opportunity to really think about how to engage with the schools in a meaningful way. So my hope was in this project to develop a sustained partnership throughout the school year and not do the typical professional development that you see out there in the elementary ed community, which is a sort of one-off summer workshop and then you wash your hands and say, I've changed the world. But rather a sustained model of you're working with that teacher over and over again throughout the school year. So the specific research questions that we're trying to develop here are, does the program of work actually impact the teacher's content knowledge? Does it actually change the instructional model they use within their classrooms? And then ultimately, does it actually have an impact on what the students learn, as measured either by assessments that we give or by the state standardized test? And so we've got a pretty extensive ability to go into those schools and collect that data, and they've granted us that permission in exchange for offering this professional development service to them. And I'm hopeful that this will be a fairly controlled experiment in the sense that experimental scientists would recognize. So I've tried to present you some of the ideas that we've used in looking at a specific cohort. This kind of curriculum design can of course be applied to anything, but my initial project was thinking about elementary ed in particular. And we've tried to think about particular ways that we present the science and how the method of delivery impacts the outcome almost as much as the content that you want to present. And in the future, we look at some other ways to go forward from here. I've had some pretty good opportunities to work with some of the folks at Texas A&M and at Texas State, which are much larger teacher preparation colleges than ours. And they've been very excited to think about adopting this curriculum themselves, and they plan to do so in the next year. And we have this potential research project in the school districts that I'm very excited about because we can actually see the impact of how this sort of focus on the teacher content and teacher pedagogy actually translates into what the kids learn. So with that, I'll thank you for your time. I do want to, before I wrap up, thank some of my collaborators in this project. Certainly, I have not been involved in this alone, and actually one of the things I find most deeply satisfying is the opportunity to work closely with all these folks and exchange ideas and have heated arguments on how best to go forward. But we have folks in the College of Natural Sciences, and we have folks from a variety of colleges in the university, from College of Ed and Sociology and College of Liberal Arts, and I've enjoyed working with all of them. Thank you for your time.